Welcome to section 5.1. Today we're going to talk about sequences, but first we're going to talk about factorials. If you've never seen factorials, I suggest you watch this video on factorials. Here's some factorials that we're going to simplify. 3 factorial over 5 factorial. 3 factorial is 3, 2, 1. Downstairs, 5 factorial is 5, 4, 3, 2, 1. So we get a lot of cancellation, 1 over 20. More typically, in this class, we're going to have to be simplifying factorials that involve a variable. So the principle is the same. On top, we've got n plus 2 factorial. That means we're going to take all the integers starting at n plus 2 and multiply. So the next one down is n plus 1, and then we have n, and then after that will be n minus 1, n minus 2, dot, dot, dot. We're going to go down to 1. On the bottom, we've got n factorial. So that's going to start at n and then go n minus 1, dot, 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 down to 1. And so again, we're getting a lot of cancellation, and the only thing left on top is n plus 2, n plus 1. Okay, one more. Let's start with the denominator, and I'm starting with the denominator because that's larger. Let's start at 2n plus 1. The next integer down is 2n. The next integer down after that is 2n minus 1. Now I see I'm in agreement with the numerator, so I'm just going to write dot, 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 multiply, keep going down to 1. Now on top, I've got 2n minus 1, and then it will be 2n minus 2, dot, 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 down to 1. And I'm getting everything on the top is canceling with all the stuff on the bottom except the 2n plus 1 times 2n. So there you go. The definition of n factorial, by the way, is n minus 1, n minus 2, keep multiplying all the way down to 1. And also, by definition, 0 factorial, you'd think it's 0, but it's not. It's defined to be 1. All right, now we can jump into sequences. A sequence is a list of numbers. That's it. There are many notations for sequence. All of these are notations for sequence. Let's find a sequence. So here we've got a sequence an is negative 1 to the n over n plus 1. Let's find the first 3 terms. So when n is 1, I get negative 1 on top and 2 on the bottom. When n is 2, I get negative 1 squared over 2 plus 1, which is 3. That's positive 1/3. And when n is 3, I get negative 1 cubed over 4, which is negative 1/4. To graph a sequence, you plot the points. So when n is 1, we have negative 1/2. I'm down here. When n is 2, I jump up here to 1/3. When n is 3, I jump back down here. And you can see these dots are getting closer and closer to the x-axis as we go out, but they keep alternating in sign. All right, we're going to want to find limits of sequences. That's what we're going to want to do today. But first, sometimes we have to show a sequence is either increasing or decreasing. Mostly, we're going to want to show a sequence is decreasing. Sometimes it's obvious. And so let's just jump down here to the rule of thumb. When is it obvious that a sequence is decreasing? It's obvious if the numerator's fixed and the denominator's getting bigger, like 1 over n. As n gets bigger, 1 over n gets smaller. If the numerator and the denominator are both getting bigger, then to show a sequence is decreasing, you need some justification. And so here's the justification I mean. To show this sequence is decreasing, what I'd like to do is use a derivative test. And I'll remind you of the derivative test. A function f is decreasing when its derivative is negative. Okay, well, I don't have a function, I have a sequence. I can't take the derivative of a sequence because a sequence is a bunch of dots. You can only take derivatives of continuous functions. So the way we get around that is we just create a function, replace the n's with x's, and then this is our function f of x. We can take the derivative of that. The difference between the function and the sequence in terms of graphs is the function is a nice smooth curve and the sequence is a bunch of dots on that curve. So if the function is decreasing, then the sequence will also be decreasing. So we're going to show that this function is decreasing by showing its derivative is negative. I've already started us out. To take the derivative, I had to use the quotient rule. and then I simplified. You can check my math there. And then certainly this is going to be negative. The denominator is always positive. The numerator will be negative as soon as x is bigger than 1. Well, that's fine. Our sequence will start with n equal 1 and then 2, 3, 4. And so that certainly shows that this sequence is decreasing. So we did it. All right. Convergence and divergence. The limit laws for sequences are the same as the limit laws for functions. And the notation is the limit of a sequence exists and is L if the terms of the sequence get arbitrarily close to L as n gets large. If the limit does not exist, we say the sequence diverges. All right, so let's find some limits. We want the limit as n goes to infinity of this sequence here. 7 minus 4 n to the 6 over n to the 6 plus 3n. Well, if I just let n go to infinity, that's negative infinity over infinity. That's a do more work. And if you remember from Calc 1, the work required is to divide top and bottom by the highest power in the denominator. So I'm going to divide the numerator and the denominator of this fraction by n to the 6th. This is the limit as n goes to infinity. I'm not taking the limit yet, so I have to keep writing the limit sign. Divide every term here by n to the 6th and write everything with positive exponents. So 7 over n to the 6th minus 4. In the denominator, n to the 6 over n to the 6th is 1. And then 3n over n to the 6th would be 3 over n to the 5th. Now I can take the limit. So drop the limit sign, take the limit. Here we get 0 minus 4. And in the denominator, we get 1 plus 0. So that's negative 4 over 1, which is negative 4. Let's do another one. I want the limit as n goes to infinity of the square root of 4n over n plus 1. Inside the square root, I'm getting infinity over infinity, which is a do more work. Limit as n goes to infinity. What I'm going to do is underneath the square root, I'm going to divide by the highest power in the denominator, which is n. So on top, I divide by n and I get 4. On the bottom, I divide each term by n. I get 1 plus 1 over n. Now I can take the limit because I'm not getting infinity over infinity. I'm getting the square root of 4 over 1 because the limit as n goes to infinity of 1 over n is 0. Square root of 4 is 2. Okay, sometimes that technique doesn't work. So here's a couple more tools in your toolbox that you can use. First, squeeze theorem. Now, I'm going to go through this sort of quickly because it's the same as the squeeze theorem we had for functions. And essentially, if we look at the graph over here, if you've got a sequence that's trapped between a sequence on top and a sequence on the bottom, and the top sequence and the bottom sequence have the same limit, then the middle sequence has to share that limit. So for example, we'll be able to show the limit as n goes to infinity of cosine n over 6 to the n is 0 by using the squeeze theorem. So what we do is we start with the fact that cosine n has to be between negative 1 and 1, because cosine, if you remember what the graph of cosine looks like, it just oscillates between negative 1 and 1. So now divide all three sections of that inequality by 6 to the n. So that implies, that's what double arrow means, that implies that I have this inequality. 6 to the n is positive, so I'm certainly allowed to do that. But then I look at the limit of this guy and the limit of this guy. As n goes to infinity, they both go to 0. Well, that means this middle guy also must go to 0. So that's by the squeeze theorem. Okay, more often you'll be using L'Hopital's rule. So again, if you're trying to find the limit of a sequence, if you find the limit of the associated function, the sequence will share that limit. Now, in this case, dividing top and bottom by the highest power in the denominator won't work, because if you divide top and bottom by n, you'll end up with the exact same fraction. So let's use L'Hopital's rule. Let's let f of x be the function ln x over x. And we'll take the limit as x goes to infinity of ln x over x. Now that's infinity over infinity. So by L'Hop, LH, if the limit of a fraction is infinity over infinity, you can take the limit of the derivatives. So this is equal to the limit as x goes to infinity. Don't use the quotient rule. Derivative of the top is 1 over x. Derivative of the bottom is 1. All right, that limit is 0 over 1, which is 0. And that does it. Thus, the limit as n goes to infinity of ln n over n must also be 0. Now, in fact, that's a limit you get to use for free from now on, as we'll see on the next page. Let's do one more, and then I'll switch to the next page. Again, we're going to get infinity over infinity. Dividing by e to the 6 to the n isn't going to work, so I'm going to use L'Hopital's rule. I'm going to let f of x equal x squared over e to the 6x. And we'll take the limit as x goes to infinity of x squared over e to the 6x. That's infinity over infinity, so I can use L'Hopital. That's the limit. I'm not taking the limit yet. X goes to infinity. Derivative of the top is 2x. Derivative of the bottom is 6e to the 6x. Uh-oh, still have infinity over infinity. I can use L'Hopital again. Limit x goes to infinity. Derivative of the top is 2. The derivative of the bottom is 36e to the 6x. Okay, now I can take the limit. 2 over infinity is 0. And so this limit is 0. All right, what limits can you use for free? These. These are all, you don't have to justify these. We've justified them all in Calc 1, so I'm not going to go through them again, but I am going to go through examples of using each one. So sometimes the sequence won't look exactly like something in that table. You have to do a little massage. So let's take the limit as n goes to infinity of n to the 1.5 over n. All right, and I'm going to rewrite that as I write it down. That's n to the 1 over n to the 1.5. Because if I have an exponent to an exponent, I multiply the exponents, and so I'm back here. Now what that allows me to do is use theorem 5, and let's see which one we're using. We're using part B. Okay, so this is, by part B, the limit as n goes to infinity of n to the 1 over n is 1, so I'm getting 1 to the 1.5, but that's just 1. Okay, next one, looks like I have something to the n divided by an n factorial. I want to use f, but first I need to do some cleanup. So this is the limit as n goes to infinity. Let's rewrite this. 5 to the 1 over 5 to the negative n is the same as 5 to the positive n. So this is 2 to the n times 5 to the n over n factorial. Still can't use f. I need to rewrite this. Limit n goes to infinity of 10 to the n over n factorial. Okay, now by f, that's 0. All right, one more. Here, I'm just going to jump back to my table. I want to use e. Okay, this doesn't look quite right because this needs to be a plus, not a minus. No worries. Limit n goes to infinity. We'll rewrite that as 1 plus negative 1 over n to the n. Part E says that works for any a, so a can certainly be negative. So this is e to the negative 1. That's by e. Okay, and that's the end of this section.